about how to find the missing mu and missing sigma, the standard deviation and mean. For the question, we have the way to solve by calculator. Mu and standard deviation is a little bit different. And I tell you, if it's more than 1 mark question, you must go for the standardized normal method, change x value into a standardized normal question, and then we set up equations and trying to solve for that. So if we're missing both mu and standard deviation, then we must set up simultaneous equations to solve for that. So if we look at example 11, limits of acceptability imposed on the length of the certain batch of the metal rods are 1.925 and 2.075. Okay, so that's the acceptable range, okay, 1.925 to 2.075. So it is observed that on average, 5% are rejected as undersized and 10% are rejected as oversized, assuming the lengths are normally distributed. So find the mean and standard deviation. So what do I know now is if I can make a diagram like this. Well, I don't know where's my mu, so say my mu is here. So 2.075 is here. And then I have the other side, 1.925. Okay, so that's what I know. So 5% rejected as undersized. So undersized must be below 1.925. This gives me 5%. And then I have 10% reject as oversized. So if it's beyond that, then that's oversized. So that's the diagram we have. Okay, that's the diagram we have. So what we can write, well, let x be the length of the metal rods. Okay, and x is normally distributed with mu and sigma squared. Okay, that's both missing. What I know is probability that x is less than 1.925. That gives me 0.05, 5%. Probability that x is bigger than 2.075. That gives me 0.1. Okay, so 10%. So probability that z less than 1.925 minus mu over standard deviation will be 0.05. Probability z greater than 2.075 minus mu over sigma, that gives 0.1. Okay, now I want to see z less than what will be 5%. So I use calculator, go for menu, just open a new page for you. Menu 553 to see the area. The area is 0.05, okay, on the left hand side of that point. With mu 0 and standard deviation 1, everything's good. So I press enter, I have negative 1.64485. Okay, and it's a couple of decimals. Just keep as many as you can. That, well, z less than that give you just 5%. Okay, z less than that, you need that step. Okay, z less than that will give you 5%. And you also see z is greater than what give you 0.1, okay, 10%. So probability z is greater than what give you 0.1. Well, instead of saying greater than what, I will go for less than what. So less than that value should give you 0.9 with mu 0 and standard deviation 1. Remember, the area we put is not the area on the left hand side, is the It's not the area on the right hand side, it's the area on the left hand side. So what I should put is 0.9 instead of 0.1 in. And then we press enter for that. I have 1.28155. Okay, z then that is 0.1. Okay, z then greater than that is 0.1. So what I have now is the simultaneous equation. 1.925 minus mu over sigma is minus 1.64485 something, and then I have 2.075 minus mu over sigma equals to 1.28155 something, and that's a linear simultaneous equation. I can just solve that by calculator. It's exactly the same as the previous question, but what's the difference is I need two area. I need to represent two area, and one of the area is greater than something. When you put in cas, I need less than something. I need that less than 0.9 is that. Less than something is 0.9. So I put 0.9 instead of 0.1. So I'll go menu 3.1 to solve simultaneous equations. I will have this out. Minus x divided by y. Okay, go up. That equals to that one. Okay, minus x divided by y, that gives you this value here. Okay, comma x, comma y. I think we put the right thing. We have x and y value here. So x is 2.00931 something, and standard deviation is 0.005. Let's give two decimal places for each of that. So mu is 2.01. Sigma is 0.05. Okay, 0.05. I think for this type of question, because you never really solve out the nice number, you always need a lot of decimals. So what I will say is most of the question will say, okay, normally part A, if it's this type of question, they will give you the question, and part A is show that mu is 2.01 and standard deviation is 0.05. So it needs to show that. So through working, I need to show. That's the show working out. And then the next question will say, use the value in part A. So you don't need to use the exact mu and exact standard deviation. So your exact mu and standard deviation is the really complex thing here. So it will not require you to really use this number here. So they will normally say, use the answer in part A, then work out what. So that's normally the question will set up. So do not want you to leave that many places, decimal places. So in this question, let's assume the answer in A is correct, and we just use this number as our mu and standard deviation for rest of the question. Okay, for the rest of the question. If the question doesn't say anything, doesn't say use the answer in part A, you will need to keep the exact all the decimals. You will need to use that one. But in this case, let's just assume mu is 2.01 and standard deviation 0.05, and then work on the rest of the questions based on this number. So Jack randomly select 8 medal rows from this particular batch and give your answer correct to 4 decimal places. What's the probability that the first 2 and the last 2 she selected were the reject ones? Okay, what's the probability being rejected? What's the probability it will be rejected for each of that? You buy a metal rose, you have 5% undersize and 10% oversize. So what's the probability being rejected? 15%, okay? So reject is 15%. Accept. What's the probability being accept? 85%. Okay, the next question asks you, what's the probability that the first two and the last two is the reject ones? Okay, the last two, you have 8. It will look like that. Okay, the first two is rejected, last two is rejected, and the middle 4 will be accepted. So what you will have is 0.15 to the power 4 times 0.85 to the power 4. Okay, so it's 0.15 times 0.85 times 0.85 times 0.8585 and then 15 and 15. So that's just 0.15 to the power 4 times 0.85 times to the power 4. So that's the probability, 0.0003. Okay, 4 decimal places, that's 0.0003. 0003. 4 decimal places. What is the probability she will select at least 4? Okay, at least 4 acceptable inside metal rolls. Okay, so at least 4 being accepted. I can make let y be the number of metal rolls being selected. So y will be a binomial distribution with 8. Okay, so you have 8 trials. You have done 8 times, and the accept rate is 0.85. Okay, being accepted is 0.85. So what I want is probability y greater or equals to 4. At least 4 being accepted. Okay, so that equals to 4. So menu 55B is the binomial CDF. I want 8 trials. Successful rate on each one is 0.85. Lower bound is 4. And upper bound is 8. Okay, upper bound is 8. So 4 decimal places is 0.9971. Okay, 0.9971. Okay, so it's a high chance to get at least 4 accepted. I can have 4, 5, 6, 7, 8 accepted. So that's 0.9971. Okay, so that's for C. For D, what's the probability that the length of the 3 metal rolls she selected are between 1.95 and 2.05? Okay, the question changed, like the successful rate change now. So I need to first find the probability that your X is in between 1.95 and 2.05. So 1.95, 2.05, and mu is 2.01. Let's just use the mu we have before for A. So, and then standard deviation is 0.05. That's the answer we get from part A. Okay, 1.95, 2.05, 2.01, and 0.05 for standard deviation. And we press enter. This rate is 0.6731. Okay, 0.6731. Okay, I have a probability of this much to have 1 metal roll selected and it's in between this length. Okay, it's in between this length. So you just use normal calculation, find out the probability, successful probability first. And you need to change to a new random variable because it's 3 trials now, it's not 8 trials. So let n be, and also the probability change as well, be the number of metros in between 1.95 to 2.05. So N will be a binomial distribution with 3 trials and a successful rate of this. A successful rate of this, but like there will be more decimals after that. I work out this by using calculator. This is my actual rate. So I will save this one. I will copy this down. Well, I want to leave more decimal places. Control VAR to define that. I give a name A here. Okay, A represent this number now. That is my successful rate. So back to the question. What's the probability? Length of these 3 meters. Oh, sorry. It's still 8. This question is still 8, and I want 3 of that. I want 3 of that to be in between that length. Okay, still select 8. Okay, still same question. Still select 8 meter rows here. So trial is still 8, but what I want is probability of success equals to 3. Okay, I want 3 to be in that range. So therefore, my successful rate has changed. Okay, my successful range changed. So menu 55A PDF is good. So I want 8, 3 to be success, and the successful rate is A. Okay, successful rate is just A because I save A as my probability. Press enter. I have 0.0638. .0638. Okay. This question, except the first one, all the rest of the question is very similar to what we have for the previous one, not the previous one, the page 9, okay, to that question. It's a normal distribution question. For a single length, you can work out the probability, but after that, we select multiple of that, like a range of that, and then that becomes binomial question. So that's exactly the same type of question we have on page 11 and combined with what we have for page 10. We're missing mu, missing sigma, we find them out, we use that value to work out the further probabilities, and then we selecting more of that, and then that becomes binomial question. Okay, so that's the type of application question you will have in the exam, okay, in the exam. Now look at the last page. Okay, the last thing we want to talk about is prepare for the next chapter. Because prepare for next chapter. Do you remember what a binomial graph looks like? Like a binomial. Going back to think about chapter 13. What is a binomial graph looks like? The dot one, right? Like something like that, right? We have 0, 1, 2, 3, 4 like that dots. Let's think about this, okay? We have this big paper. Okay, look. This. Okay, this big paper. I also plot any graph I mentioned on this one. Okay, so if it's with the correct scale. For example, if I want to only label success of 5 times, well, I only have trial 5 times, I can put 0, 1, 2, 3, 4, 5, right? With even space, like 5 times, and with the probability, whatever is that. Think about if I have 10 trials, well, all the distance will be halved, right? 1, 2, 3, and then 10. Think about if I have 100 points, what will happen on this paper? Like, N is 100. What kind of graph you expecting? They close to each other, right? They even close to each other. And then think about if I have 10,000 points, like success of 10,000, what will happen? they will really connect, like close to each other. And what it will look like is more like a line. It's actually still has space in it, like 0, 1, 2. It's still separate points. But what it will look like, it will like connecting together. Okay, if you use the same piece of paper, trying to sketch more and more trials, all the dots will be really close to each other. And when you look at it, it's still dots, but you will look like they're connecting together and then forming some shape. Okay, so just you don't need to know why and how, but you just need to know that if I want to sketch a binomial random variable, like for a really large number of trials, okay, for a really large number of trials, like the more the better, the final graph you sketch will look like a normal distribution. Okay, will go similar to a normal distribution. You know there are different things. One is discrete random variable, but the other one will be a like continuous random variable. They're not the same thing. The graph is not actually connected, but as I said, when you sketch it more and more, the graph will tend in, like you look at it, it's more like connecting lines, and then they are all next to each other. So the graph will look like a normal distribution graph. Okay, so that's the idea we have for this exercise. So what we talk about is when we get n is sufficiently large, binomial random variable x, okay, binomial random variable is x, binomial distributed NNP, right? What's the expected value for x? Just normal, it's a revision. NP. What's the standard deviation for x? And square root of that. Okay, standard deviation, that's the variance. Standard deviation is the square root of that. Okay, that's for binomial. Okay, how do we calculate binomial? We calculate binomial like when x is greater than 3, so we want 4 to n, right? And then we put in calculator and then do that. Okay, so when we get n is large enough, okay, how large is large enough? We give restriction. When np and n times 1 minus p, they both greater than 5, then we say it's large enough. Okay, what is large enough? When np is greater than 5, n times 1 minus p is greater than 5 as well, then we say n is large enough. But it's still not that enough, okay? So that's the minimum requirement, but I don't think it's working still. But it needs to be even larger than that. Okay, so thousands of n will be a good size. We use normal approximation. Just a little hint for special students, just let you know, any distribution in the end, when n get large enough, will all tend into a normal distribution. So normal is the most interesting one. Okay, everything when n large enough will all tend into a normal distribution. So this is the central limit theorem in uni we learned. Okay, so everything trying to make a shape of like a normal when n get large enough. Okay, anyway, back to this one. So for binomial, okay, the graph, as I said, in the end looks like a normal distribution curve, like a curve, but there's still dots. But we can say what? We can say x is approximate. Well, you don't need to write this right? Like I just tell you, it's not exact. It's approximately distributed as a normal distribution. Okay, it's a normal distribution now. It's approximately normal distribution. But with what mu and what standard deviation? You know that for same x, your mu is not going to change. Okay, your mu should stay the same. Doesn't matter whether it's approximation or exact. Your mu should be your mu. Right? Like it's not say I change from this distribution to that one, your mu change. It's not going to change. So your mu is still n times p in this case. Okay, mu follow the same mu as before. And your standard deviation is square root np1 minus p. And then we square that because that's the place for variance. Or you can still just write np1 minus p. So that is your variance. So what all I talk about here is normal can be treated as a binomial can be treated as a normal question with the same mu as before and same standard deviation as before. Okay, it will center at the same place and with the same size of spread. All right. The other thing I want you to know is if anyone decides to learn probability in uni, what we learned today is not correct. Okay, so you need to adjust something, but I'm not going to talk about adjustment now. Like there will be a correction here, but it's not correct. But that's how we teach you now. Okay, so just do the simple way. This is the simple way, and it's not very correct, but anyway, I don't care. Okay, if you learn probability, your uni teacher will help you to fix that, and it's not my problem. I have to tell you that.
Other one's wrong because it says n bracket 1 in p minus p and p bracket 1.
No. The NP 1 minus P is the...
Like on the version.
This one?
Yeah, is that different from the other one?
That one?
But from the NP 1 minus p.
So 1 is the standard deviation. 1 is just the checking whether it's good to use normal approximation. It's the two different things. It's not say your mu is greater than 5 and your standard deviation is greater than 5. No, it's just your checking requirement. You need to check that. If that works, then it's good to use normal approximation on binomial. But if that's not greater, then it's not. Okay, so don't blame me. I'm not teaching you wrong. Like, yes, I'm teaching you wrong now, but like, it's not what I want. But that's how you should learn it now. Okay, so let your uni lecturer fix that. So what we have now is an examination consists of 25 multiple choice. Each have 4 answers, and at least 10 correct answers are required to pass the exam. Okay, at least 10 correct will make you pass the exam. And suppose that a student guesses the answer to each question. Well, this student is really not that good. Okay, so you shouldn't get, at least you need to know 5. Can't guess all of it. Okay, what's the approximate probability that the student will pass the examination? Well, just make sure you understand that if no one asks you to use approximation, there's nothing indicate approximation. You still use binomial. Okay, do not try to just use normal. Okay, so this is not the thing we like to do. We learn this because next exercise, next chapter, we need this skill. Like we need that. So that's why we learn it. But most of the time, we don't like to use normal to do binomial. This is a binomial question. I hope you can see that. 25 trials, each trial get a successful rate of a quarter. I want 10 success, right? Let's have a look. What's the difference between the exact probability and the approximation probability? So let X be the number of correct answer. Number of correct guess. Okay, so X is actually binomially distributed with 25 and a quarter. Okay, actually normally distributed. So my expected X is 25 on 4. My variance of X is 25 times a quarter times 3 quarters, NP 1 minus P of 3 quarters. And what we have for the variance is 75 over 16. Okay, 75 over 16. And standard deviation is square root of that. And that's 5 root 3 over 4. Okay, that's like, doesn't matter what you have, normal or binomial, you still have the same mean, same standard deviation, and I need to calculate that out first. Okay, 25 times a quarter is 25 on 4. Variance is 25 times P times 1 minus P is 75 over 16. Standard deviation is the square root of that. We have 5 root 3 over 4. Alright, now X is approximately, you know what, in the multiple choice questions, sometimes they ask you to use normal approximation to do things, so it's not really instant response. So in multiple choice, you need to work the same way as what I'm doing here. If they said use normal approximation, you need to use normal approximation. So it will be approximately a normal distribution with the same mean. Okay, that's my mean. And my standard deviation is 5 that, and then we square that. Okay, this is a very trick point here. There's a very trick point. Let's think about the exact probability first. What is the probability that we'll pass the exam? Okay, exact first is the probability your x needs to be greater or equals to 10, right? That's your exact probability. Oh well, I'm not putting in calculator yet, but what I need is x greater or equals to 10. So what I'll put in the calculator is menu 5 B, binomial CDF. So I have 25 trials. Successful rate is 0.25 because it's a quota. Lower bound, at least I need to answer 10 questions right, and I need 25. I have 25 as maximum. So that's my exact value of passing the exam. So that's leave how many decimals you want? 4 decimals. Let's go for 4 decimals. That's 0.0713. Okay, that's my exact rate. Use binomial to calculate is the exact rate. Let's look at the approximate rate. Okay, I still need x greater or equals to 10. But remember your mu is 25 on 4 now, and your standard deviation is 5 root 3 over 4. You use normal to calculate that. Use normal to calculate that. So because it's the approximation. So you go 552 as normal CDF. Okay, your mu is 25 on 4. I will just type that in first. And your standard deviation is 5 root 3. 5 root 3 over 4. Okay, lower bound, I need to answer at least 10 questions correct. Okay, at least 10 questions correct. What is my upper bound? What is my upper bound? Infinity. Okay, that's the part I want to tell you. We ignore the actual domain, like the practical domain for the question. If it's a normal, we don't talk about domain anymore because this is the question on your book as well. And if you put 25 and if you put infinity, the answer will be slightly different and will be a couple of decimal different. And that's last year the student asked me why I'm a little bit different compared to the book answer, and then I said, what do you put as your upper bound and lower bound? Said, 0 and 25. I said, no, you should put negative infinity and positive infinity as your lower or upper bound. So that is the thing you need to pay attention, even though we can only answer 25 questions right, but in this case we said infinity. Okay, 10 to infinity, that. So what's the answer? 0.04163. Do you think it's accurate? Do you think it's good? It's 3% different. It's a lot. Okay, it's a huge amount of difference. Why? What's the reason? Well, I will tell you the first reason is because it's not the correct way to do it. There needs to be a correction here. It shouldn't use 10. I think it should use 9.5. Okay, instead of 10. There's the correction we have. Don't want to talk about the reason. Actually, if you use 9.5, it will improve the answer a little bit. And the second reason is the number is not big enough. Okay, 25 is not a good size to use as the normal approximation. It's like too small. Even though it satisfies NP greater than 5 and N1 minus P greater than 5, that's, as I said, it's the minimum requirement. Okay, that's the least requirement you need to follow. But it's still not good size to use as a normal. If you have 250 questions, the answer will be improved a lot. Okay, let's do the next one. What is the approximate probability that the student gets from 12 to 14 questions correctly? Okay, so B we want exact. So it's the probability that X is in between 12 to 14. You need to include 12 and include 14. It is 12 to 14 correctly. 5B. I have 25 trials and successful rate is 0.25 and lower bound is 12 and upper bound is 14. We click enter, we have 0.105. Okay, so let's look at the approximate probability. That's the probability. Well, we have the same notation here, still the same thing. So what we have now is binomial normal CDF. Lower bound we have is 12. Upper bound we have is 14. Well, not 14, sorry, 14. Okay, all the rest will be the same. Okay, all the rest is the same. Press enter. That's 0.0038. Okay, 0.0038. It's still quite a big difference here because 12 and 14 are not the correct number to use. You should actually use 11.5 and 14.5 in this case to improve your answer. But again, one of the reasons is not the correct way. The second reason we don't use it is because 25 is not large enough to do normal approximation. And you can see the answer is not very correct, but that's the way how you do normal approximation. Okay, that's the way how you do normal approximation. Alright, that's the end of chapter 16. Any questions? Okay, no question. Print chapter 17 and we'll start that on Monday. Okay, we'll start that on Monday.